I brought 4 presentations with me with different coloured backgrounds because I've never given a lecture in a tent before and I wasn't quite sure what would fit. And whether so I may change it halfway through and change the background as the light goes down. I've also, I don't think, ever tried to give a presentation to a mixed audience where you are scientists, so you're going to know much of what I'm going to talk about, but it's also open to the public. And with a subject like this, you can't just dive into it. So what I'm planning to do is to spend the beginning of it saying something about elements and radionuclides and radioactivity, maybe extremely familiar to many of you, may not. Then eventually, I promise you, I'll get on to radionuclides, unstable atoms in the ocean. And I thought I'd start with this. I've always felt, if you read the back of that thing, you will say, now here's a guy who hasn't decided yet what he wants to be when he grows up, and that's true. So it's very appropriate that I'm talking about this subject. Scientists would refer to it as radioecology. Actually, if you look in the 2-volume Oxford English Dictionary, the word doesn't exist. There is no real subject of radioecology. It's a bit of this and a bit of that. And the reason I decided to call it unstable atoms is I felt if I said it was radioactivity or radiation, you're going to expect a lecture about nuclear power, nuclear submarines, pollution, and so on, because that's what people think about it. But in fact, it's a much wider subject than that. I still feel it's a subject that's never grown up. There are lots of different aspects about it. Much of it has been based on observation, rather than having some theories and then doing some experiments or observations to see how they relate to them. It is yet to mature, I think. So this is going to be something of a theme. Often get into conversations with people about, well, how many naturally occurring elements are there on the Earth? And then I get into a discussion about, well, what's an element? You know what an element is, it's the atoms. There's never a good representation of it, I don't think. Well, you can't be. Essentially, it's a nucleus, neutrons, protons, and a cloud of electrons around it. What makes an element, of course, is the proton, the number. Elements have a fixed number of protons, for those of you who don't know it, a variable number of neutrons amongst the protons in the nucleus, and they form different isotopes. I usually refer to them as nuclides. There is a subtle difference, but because of my background, I usually talk about different nuclides. So as you go up the atomic scale, you've got hydrogen with 1 proton, helium 2, lithium 3, and so on, and up the periodic table. The number of neutrons simply in the stable form can be quite variable, but the number of possible isotopes just gets bigger and bigger and bigger. And nowadays we can make them, and you go up to about 3,000 different isotopes of various sorts. I'm not quite sure what I'm pointing this out. Where do the elements come from? It's amazing how recent it is that we've really got a reasonable idea of where the elements come from. Some of them, very few of them, come from very large stars like the Sun. Not giant ones, but large stars like ours. And you just think of it as a ball in the sky. And actually you can, with various instruments, sort of more or less start dissecting the Sun. And it's a very interesting animal, I think, floating around. You can cut it up into different bits. What's going on in the Sun is that the light elements are being fused together. So you've got hydrogen, helium, and it makes a bigger atom and gives off energy. That's the main thing. Hydrogen, tritium gives off helium. And it's an exporter of energy, and that energy comes to us in the terms of heat and light. And if you could section through the Sun, you've got increasing elements being made. Hydrogen on the outside and helium, carbon, not necessarily in the right atomic order. And bang in the middle, iron. Iron is an incredibly stable element, number 26. Beyond that, if you want to bang these atoms together to make bigger elements, you don't have an excess of energy, you actually need energy to do it. Our Sun will eventually go up into a red giant. And when you've got a red giant, you can then go beyond tin. You start creating heavier and heavier elements. But to create the really heavy elements, you need something magnificent, a supernova explosion. There is then enough energy to actually do it. So all of the elements that we have on Earth actually come from quite different parts of the universe. And I always think it's a very good chat-up line. Not that I'm past this now, but I used to think it was a very good chat-up line. If you're sitting next to a lady at a table or something, you just happen to hold her hand, And you say, oh, you know, she's got a bit of jewellery, a bit of silver or a gold ring or something, and usually a stainless steel watch or something. And you say, do you realise that the atoms in that piece of silver or gold came from a totally different part of the universe from the atoms that are in your watch? When the solar system was formed, there was enormous explosions. All these gases and clouds came together, condensed, formed the sun, the planets. Our planet condensed, all these elements recycled, dug up, and so on. And there they are, they end up on your hand 4 inches apart. Isn't that incredible? What's even more incredible, how do we know that? And then you can spend the next half hour explaining all of this. You see, anyway, so the elements on Earth come from totally different parts of the universe. And as you go up through the elements, you need more and more neutrons in with the protons. So the low end, they're sort of more or less equal balance. Eventually you end up with a ratio of about 3 to 2. And if you look at that diagram, all those little black dots are the stable elements of the different elements. And the cloud around it are all the unstable ones, which are either natural or unnatural. But there's a rather interesting break at bismuth. It was always thought that bismuth was actually quite stable, and if you're taking bismuth, you've got indigestion, as you may well do by the end of the evening. It's rather strange to think it's radioactive. When I say radioactive, for those of you who know about half-lives, I'll come on to it. It's got a half-life of 19 times 10 to the 18 years, which is about as stable as you go, but it's just over the edge. It just is not quite stable. Everything above it, however, all those elements are completely unstable. There are no stable forms. The other interesting thing is going up to there are 2 holes in that table. One is technetium and one is promethium. The longest lived technetium isotope, it's got a half-life of 4.2 million years. The other is promethium, and the longest lived that is 17.7 years. So those 2 don't exist, effectively. They're just totally decayed away. We've made them since, but at the moment, when the Earth was formed and naturally out there, they simply don't exist. Now, the point of all of this is for the unstable ones, they're constantly trying to be stable. They're seeking stability in one way or another. And the various ways of doing this, you can convert a neutron, if you've got excess neutrons, you can convert it into a proton. And here we have the quarks. You know, we've all heard about the quarks. There's a whole sets of quarks. I think we want to do a children's program with all different sort of quarks. You get a nice bit of music with and so on. But the trick is the neutron will turn one of its down quarks into an up quark, just like that. It's good, just like that. Within the proton. And the reverse can happen in that an up quark can turn to a down quark, goes back into a neutron. These sort of things are happening all the time. Another trick that atoms have to get stability is they will capture one of the electrons going around it, as beryllium does, for example, and then convert a proton into a neutron. So they can change that way. So in terms of decay, I think people always think when they think of atoms decaying is that they decay to something lower down. But actually, if you convert a neutron into a proton, it goes up the periodic table. It goes up 1. The other 2 forms, it goes down 1. They're quite interesting transformations. Another transformation is the emission of an alpha particle. The really heavy ones, to seek stability, will belt out a combined pair of neutrons and protons. Actually, there are about 20 odd different ways in which radionuclides disintegrate and in the seeking for stability. But this is enough, I think. You get the idea that unstable atoms seek stability by changing within. And just to summarize that lot, we've got a neutron going at a proton, proton to a neutron, the electron capture and spitting out an alpha particle. This usually results in quite an excited atom, and I can see you're quite excited yourselves just listening to all of this. And these excited atoms then get rid of this excess energy by emitting gamma rays. And they emit gamma rays in very precise energy bands, and that's extremely useful in measuring them. Now, each radionuclide has a unique half-life. In other words, there's a fixed period of time. For any one atom, you don't know when it's going to actually disintegrate. If you've got enough of them, over a fixed period of time, half will go, then another half of that half will go, and so on. So it goes away exponentially. After about 7 half-lives, you're down to less than 1% of what you started with. After about 10 half-lives, you can more or less forget it. You can either represent it on a normal scale, or usually it's done on a log scale like that. That's not the end of it, however. The big, heavy atoms, if they just get a neutron, they literally just fall apart, fall in half. That's nuclear fission. So uranium-235, which is quite common out there, as I'll get on to in a minute, absorbs a neutron, goes up to 236 and falls apart into two sort of more or less equal parts, not quite, and it'll shove out more neutrons. And if you get it right, you can get a chain reaction. If you get it really right, you get an explosion. The difference between the two is really quite exciting, but not easily done. There is one place on the planet, in Central Africa, Oklo in Gabon, where there's enough uranium in layers for this process of fission to actually go on. And this is one of the few places on Earth where you can get some of these more exotic elements which arise as a result of what's happening to uranium. But usually it's like back during Camel, this great big element falls into two. But there's another trick. It can capture a neutron and it convert it into a proton and go up the periodic table. And this is where we get beyond uranium. You get 238 uranium, go up to 239, goes up to neptunium, which is the next one up, then to plutonium. And that actually happens at Oklo. And it takes an awful lot of chemistry to see it happening, but it is actually happening. And it all starts off with the 238 uranium because it's extremely long-lived. Yet another way in which these unstable atoms are out there is from the cosmic rays coming out of the sun, mainly electrons and neutrons, and from deep space. From there we get the protons, alpha particles, electrons and so on, and they are belting the Earth all the time. The Voyager spacecraft is just reaching the stage where it's going way out into this field, and it's being belted. It's just going beyond the edge of the solar system. It's absolutely being thumped with cosmic rays. I think they're wondering what's going to happen to it. So come back to my original question. How many naturally occurring elements are there? Well, stock answer, 92. It's always 92. My granny would probably, well, no. But no, yes, it's 92. Okay, well, really, which ones of them? Are we talking about elements 1 to 92 or 92 elements? Because what about technetium? What about promethium? And what about the extra ones I've talked about? Forget about the elements, just look at the unstable atoms. The Earth is composed of about 339 isotopes, which are nicely grouped into elements. Of that, 255 are stable. 33 of them, more or less, have got half-lives which are more than 80 million years, so stable as far as I'm concerned. Which gives us 288 primordial nuclides. They were there when the Earth was formed. I'm not sure I'm pointing this out. What am I pointing? Right, and we've got 51 short-lived nuclides. So we've got about 85% stable and 15% that aren't. So in terms of the planet, about 15% of the basic building blocks that make it up are actually unstable. 50% of you are unstable. You're trying to walk along, you start falling apart. But that's what the globe is, roughly 15% unstable. The other thing before I get onto the subject, is that an element isn't just one or the other. If you've got something like potassium, then a very small fraction of it is unstable. Most of it is stable. If you've got an element like rubidium, which is quite important, then about 28% of it is unstable. Even calcium, which you think of as being quite stable, has got one unstable isotope. Less than 1%, but calcium is slightly radioactive in its natural form. So what about these ones that are all unstable? Once you get above the bismuth, which you may or may not regard as stable. Well, they all come from the very heavy elements. They decay in various complicated ways. So you get elements like astatine. You can calculate that quite well. At any one time on Earth, there are 28 grams, more or less, of astatine. I wouldn't ask you to go out and look for them, but you can do the calculations quite reasonably well. There are about 23 grams of astatine, 28 grams of astatine. Not a well-studied chemical element, as you might imagine. Apart from anything else, it's so intensely radioactive, you can't really do anything with it. Right, and that's the sort of picture you get. You start with uranium. It can go to pieces in all sorts of ways, and each element, each isotope of uranium and thorium disintegrates like that. So, back to my question, how many naturally occurring elements? Yeah, 92. I would go along with 92. 1 to 42, 44 to 60, and 62 to 94. That's my answer to the question. If all of that wasn't enough, all of these are naturally occurring things. To that, we've added unstable atoms to the oceans via the atmosphere. First of all, with atomic bombs, which is the big atoms falling apart, and they could produce really wonderful clouds. The French, this is what started me interested. Here are Murat, these enormous explosions going out, bang in the middle of the Pacific Ocean. Then after that came the hydrogen bombs, which is taking the light elements and fusing them together. And they really were spectacular and spreading material all over the place. So let me get into the subject properly. And let me clear one thing too. Radioactivity is a phenomenon. Radioactivity is when these atoms fall apart. And it's measured in becquerels, which is 1 disintegration, 1 nuclear transformation per second. It's not the same as radiation. When you read the papers, everything we'll have read about Fukushima and even the BBC News, I can guarantee virtually all the terminology is wrong. And it's very, very difficult to understand it. Ionizing radiation are these bits that come out, the alpha particles, beta particles, neutrons, gamma rays, X-rays. That's what radiation is. That's not radioactivity, that's radiation. And dose is a different thing again. That's the energy that's absorbed when these things come out. Quite different things. So if you go at last into the sea, these are some of the naturally occurring radionuclides in seawater. Becquerel per litre, 1 disintegration, 1 transformation per second. Top of the list is potassium-40. And then through rubidium, uranium, radium, lead, and so on. If you look at the inventory, in terms of terabecquerels, there's an awful lot of potassium out there, 10 to the 10. Rubidium about 10 to the 8. In fact, there are about 4,000 million tons of uranium in seawater. That's an awful lot out there, 4,000 million tons of uranium. You worry about what's discharged from power stations, 4,000 million tons out there, quite naturally. To that, of course, we've added the fallout radionuclides from these weapons tests and so on. The last test was a Chinese one in 1980. Within about 4 or 5 years, most of that had hit the ocean surface. And you can work out then the inventories that went into the north or the south, very considerably less than the amount of radioactivity that's already there. So when you talk about radioactivity in the oceans, the vast, vast majority of it is naturally occurring from all these unstable elements. Even the weapons tests, the snaps, all of the power stations have not added much to it. Of course, there are local additions, as in coming out of nuclear power stations. Very, very, very little. Perhaps a bit more from nuclear power reprocessing plants like Sellafield, but again, compared with everything else, they really are extremely small amounts. So, getting back to my Peter Pan theme, if these unstable atoms are decaying and they all decay at fixed rates, then you can actually use them as clocks, and they are used as clocks. And they're particularly useful if they emit gamma emissions because it's relatively easy to measure. Probably the clock you know more about than anything else is carbon-14. And that comes from way up in the atmosphere. And that comes from the neutrons streaming at us primarily from the sun. They're hitting the nitrogen in the upper atmosphere and forming carbon-14. About 7 kilograms per year of carbon-14 is formed up there. And then it gradually comes down, settles on land, the ocean surface, taken up by living organisms, including you and me. And then you can look at the ratio of that compared with the carbon that hasn't come from up there. Fossil carbon in particular, the reason we know in relation to CO2 in the atmosphere that it's being driven by emissions from fossil fuels is because of the change in the ratio of the radioactive carbon to the stable carbon, because coal in the oil doesn't have any carbon-14 in it because it's got a half-life of 5,730 years, so 10 half-lives. As I said, you can forget it. Carbon-14 is being used a lot. It's because of that half-life, it's very useful for looking at the turnover of deep water in ocean basins around the world. The other end of the scale, the tritium that's formed up there, got a half-life of just over 12 years, hits the sea surface, and you can see the rate at which that tritium is being subducted down, mixed down from the surface. This is a profile of tritium in the Pacific Ocean in a section like that, and you can see the red, the tritium, you can see the areas where the surface water is being mixed down deep, and the areas where it isn't, where it's being subducted in various ways. Even the stuff coming out of reprocessing plants and nuclear power stations is quite useful. One of the pairs of nuclides that were discharged by Sellafield at one stage in quite considerable quantities were cesium-137 and 134. One has a half-life of just over 2 years, one a half-life of just over 30 years, and they're quite reasonably water-soluble. So they're coming out of a point there on the Cumbrian coast, which are probably if you probably can't see it, coming out there. Le Havre was also discharging some as well, but you could look at the contours of the cesium in the sea, and you can then, what we tried to do is to work out the transit time from there up to the North Channel using the ratio of those two isotopes. So if you look at 137 divided by 134, coming out of wind scale in the early 70s, the ratio was about 5.76, would vary from year to year, 4.9, 4.1, which is quite handy because we thought the transit time from the modelling was a year more or less, and if you actually took the samples across that North Channel, then you got those ratios, and by using those ratios, we got estimated times of transit from about just under a year, 0.86, up to about 1.24. So very useful clock to see how these big water masses were moving around the Irish Sea. One thing I haven't said is when a radionuclide will quite often decay to a daughter, we always call it a daughter, not a son, I don't know why, which is then itself radioactive. And the daughter, in terms of radioactivity, the half-life of that could be shorter than, the same as, or longer than the parent. So you can use these ratios as well. And they've been used very much in relation to looking at processes at the seabed. Near the coast, you've got 238 uranium, and it decays eventually to thorium. Uranium is reasonably soluble, thorium isn't, so it's taken to the seabed. But seabed's got thorium in it anyway, and that decays to radium. Radium is reasonably soluble, and it goes back up into the water. However, that other isotope, radium, decays into another isotope of thorium, which has other things taken down again. So it's going up and down, up and down. Each nuclide with a different half-life. So looking at the ratios of it, you can work out the rate at which these things are happening quite reasonably well. One of the daughter products is radon, which is a gas. So you can see the gas coming out of the sediment and the exchange with the atmosphere. The radon turns into lead, which obviously is not very soluble and goes all the way down again. So again, using these isotopes and these parent-daughter relationships, you've got a wonderful inbuilt clocks for what's happening throughout the oceans. Chemistry, to determine them, isn't always that easy, and the theory doesn't always mix the practice, but you can see lots of things happening. And that is just a table to show you the combinations just of those unstable above 83 elements. Their isotope ratios can be used in all these sorts of ways to look at all sorts of processes, and have been used, that are going on in the oceans. Just to show that it works, for example, you've got 234 thorium, you've got it on the surface, there's more there than has come from its parent, so it must have come down from the surface, and it's then mixed down. And you can see two profiles here, quite different. On the right, it's got a 24-half-day half-life, so it's been mixed down very rapidly, one part of the sediment, very slowly in another. That's over a short period of time, 24 days. Fortunately, there's another similar isotope, lead, which has got a half-life of 22.3 years, and again, you can see that being mixed down through the sediment. Chasing these things in the ocean is quite easy. We had quite interesting problems at Sellafield because we could find plutonium, which we knew was coming from Sellafield, deep down into the sediment. And just off Sellafield, there was a huge mud patch, which is acting like a great big sponge. Now, to examine this, you need a decent-sized boat. This is the Cyrilana, which was about 240 or 50 foot long. I forget, that was a scrap, but she was a nice big ship. And using that, we could throw all sorts over the side. There was a bit of science I really loved, particularly if the weather's like this. I bet you're all jealous of the weather like that. Used to throw over box cores and take samples down to a few centimetres and so on, and look at the plutonium down there, and still it kept going down. Then we had nice long cores, and you drop those very carefully over the side and belt them down. And we saw that the plutonium was going down about 1.5 meters. What's it doing 1.5 meters down? Depending on which samples you took, the quotients, which is the ratio of the plutonium isotopes, the long-lived to the 238, were much younger than you expected. So what's happening? How did all that plutonium get that deep so quickly compared with those other profiles I was showing you? And you looked at the biology with these grabs and couldn't see anything particular. So you go deeper. Was the core contaminated? So when it goes down, when it hits the surface, it then drags the sediment down, and therefore you're getting a mixed tube. Well, we did that, played with it, take the tube out. We even wired the tubes to see what would happen in terms of compression as you went down the tube. And eventually we really got hold of a decent job. This is the sort of sedimentology I like, and put down a casting, a great big chunky rod thing. Very, very difficult to handle on board, as those of you will probably know, and getting it inboard. But when you can then take the sides off it and dissect it. With my biological origins, I always loved dissecting things. So I used to dissect it to see what the hell was in it. And you used to get these very strange tubes and so on. And eventually emerged this. And what is it? And what on earth is it doing 1.5 meters down? We looked at it for some time and wondered what this was. I thought of all possibilities of selling it. But there it is. It's quite a large and interesting looking thing, and it's a lovely colour green as well. And I'm sure there's a market for it somewhere. And it rejoiced in the name of Maxmuleria lancasteri. It's an echiuran. It was only found in that part of the Irish Sea, and as far as I know, further up the coast. I'd never have known what it was if I have a friend, Pete Gibbs, here in the MBA, who identified it for me. And what this thing does, it sits down in a burrow 1.5 meters or so, and it's got this on the right there. It's a proboscis, and it comes up the tube at night, apparently, and it puts this proboscis all along the sediment surface, and it's like a channel, a cilia, and it takes up all the plutonium-contaminated sediment on the surface and takes it down into its burrow. And British Nuclear Fuels didn't pay it a thing. I mean, it's not, they haven't got it on their logo. I mean, they haven't got to preserve the Maxmuleria lancasteri Society, nothing. And it does this absolutely superb job. And we knew that eventually with this big core, dissecting the bits out. So if you looked at the ratio, you could see what it was on the sediment surface, then in the gut contents, then in the lining of the gut, because it dragged it down. And then in the animal itself, and then in the adjacent sediment. You can see where the animal wasn't, the ratio had got to about 14. Where it was about 4. So it's this animal taking the stuff down. So that was quite interesting. We used to throw lovely things over the side of the ship. These current meters, I think I was looking through my old photograph, a flying bedstead. Throwing flying bedsteads over the side of the ship was wonderful. This was to look at the strain of the water on the surface and at different heights above it, and looking at the near surface stress to see how it was belting things along. And we always top the whole thing off with a big donut to say we've got instruments under here. And I remember one day we were just sailing away, and you could see on the horizon a fishing boat had pulled up, was busily hauling all of this lot back on board, presumably to get compensation. We had put the thing down about 15 minutes earlier. Lovely days, not always that calm, of course, yeah. Out in the Force 10 going along, but lovely days nevertheless. Is it getting up? Right, now, back to me Peter Pan. That's clocks. How about tracers? Well, some of what I've told you, of course, involves tracing things. But we used to do quite a lot of collaborative work with the French. And it was very useful to look at what had come around the bottom from Windscale, what was coming out of Winfrith, which was on the south coast, and what was coming out of Le Hague. And there was some considerable argument as to which coast was being contaminated by what. But fortunately, Le Hague was shoving out something fairly unique, which was antimony 125, and that was a wonderful tracer. You could trace the water as it came around Le Hague, Cap Le Hague, which is, you can't see it there. As the water came along and then took it up the channel, and you could see the water months rattling up the channel. And again, go along to all these wonderful mathematicians and say, I don't think your model's quite right, because it never seemed to fit what it was that we observed. One of the great things about looking for traces was what could you trace something in? Usually useful to have something that was stationary as something went by. And an awful lot of use was made in the 70s and 80s, perhaps still is, with fixed seaweed. I've always been particularly interested in these missing elements, the technetium, the plutonium, the americium, elements which biology's never ever seen before in its evolutionary history. And the technetium, because it never had existed, we weren't quite sure what chemical form it was, but everything told us it would be in the pertechnetate, technetium-7, it would be highly soluble. And the things which stuck to seaweed were, as you might imagine, the things that by and large not soluble. The last place you would look for technetium would be seaweed. There always seemed to be some extra beta counts of this stuff we could never really account for. And this used to drive us mad. Eventually, we found that fucus absorbs technetium to a very, very high level, about 15,000 times the level in the water, even though it's highly soluble. That was like no other element that we'd ever observed in relation to fucus seaweeds. And then started looking at all sorts of other things. We looked at the crab, Cancer bigurus. We looked at mussels. Mussels are usually pretty good at picking up things. Concentration factors nowhere near the fucus. And we thought there was something really peculiar about this seaweed. Had we got it right? Were we doing the right things? Because you had to chemically separate out the technetium, which itself wasn't easy because you don't have any traces because it didn't exist, and then do beta counts on it. And I really thought we'd screwed up on this until we looked at this animal. And when we analysed that really soaked it up compared with any other animal. Now, why should a lobster compare with a crab? Has never seen technetium in its evolutionary history soak up technetium. I got some quite expensive isotope to do some experiments with, and the lobster took it out of the water within a day or so, and that was the end of the experiment. You know, to sort of ring the lobster and put the technetium back in again. It was very difficult to do these experiments. However, we persevered. One of the things that we were able to do, we had to get an isotope of technetium that emitted gamma rays, because if you've got a gamma emitter, you can put it between two crystals and you can measure the animal or the plant or whatever it is while it's still alive. So you look at the rate at which it is taking up an isotope and the rate at which it's getting rid of it and still alive. You take it out, put it back, put it down. And of course you need a lot of lead around it to cut out all the background radiation. And I think Colin Wasling there, I think he's putting in some fish eggs between, the only photograph I could find, between two crystals to do the counting. So we did quite a lot of experiments over the years, particularly with the poor old place. I must have dissected hundreds of them and looked at radioisotopes going in and out of them. So it was a turn to look at it in relation to technetium. Well, you put place in the water with labeled technetium, and it gradually accumulated it to about 5 to 10 times the water, okay? Well, because we were not sure about the environmental observations, I stuck a shrimp in, ran out of radioisotope after about 30 days, but that was somewhere between 5 and 10. And as I was saying, I shoved the lobster in, they just soaked it up so fast it was the end of the experiment. So, well, what is it inside a lobster that soaks up this element that it's never seen before in its evolutionary history? A very good question. We did eventually some more experiments with crabs and lobsters, comparing them. And you think you're looking for an organ that really soaks up this weird element. But every tissue in the lobster, you look at the gills compared with the crab, the shell compared with the crab, the hepatopancreas compared with the crab, the claw muscle compared with the crab. Crab hasn't got a tail muscle, but if it had one, I'm sure it wouldn't be very high. Every tissue in this lobster soaks up this element it's never seen before. Not entirely sure why. It always seems to be related to metallocyanin, but to be honest, we just never ever got to the bottom of it. The only thing is the Norwegian lobster did much the same, but I couldn't find any other crustacean that did it. Now, it's a photograph of a tuna. You think, well, I've got that. Because we had this big setup at Lowestoft in terms of being able to do tracer experiments with live animals, of course you could get radioisotopes of other elements of interest. And a big issue that we were faced with at one time was mercury in tuna. There'd been a big scare in Japan, Minamata, where they'd been discharging mercury, and a lot of the population got down with mercury poisoning. And then everybody was looking everywhere for mercury. And it was found in tuna in very high concentrations. My God, the whole of the world's oceans are polluted with mercury, methyl mercury, this organic form, dreadful. Could this be true? And we were asked if we could couldn't do experiments on tuna, but we could do some experiments to try and solve this issue. Well, if you put mercury in seawater, either organic or inorganic, they would take it up quite well, back to place. But it would take up the organic form more than any other. So I got there on the left the non-methyl form and the methyl form. The food of the fish seemed to have about 30% non-methyl and 70% methyl mercury, so quite a clear ratio. When we did the experiments, and we used radioisotopes to do this, then if I go down the left-hand column, the place absorbed about 10% of that 30%, but put very little of it into the muscle. It went into various organs, into the kidney, the gut wall, and so on. And it excreted it quite quickly, with a half-life, biological half-life similar to a physical half-life, secreted it fairly quickly. When you fed the fish the organic form, the methyl form, they absorbed 90% of that 70%. 80% of it went into the muscle, and it excreted it very slowly. So if you looked at the ratio in the fish compared with the worm, then 95.5%, over 95% of it was methyl form, and mainly in the fish's muscle, and less than 0.5% was inorganic. That had nothing to do with pollution, had nothing to do with bacteria converting it from one form into another. It was just the physiology of the animal, separating out these two things. And because it had a long half-life, of course, it was excreting it slower than it was taking it in. So simply looking at the kinetics of it, which we were able to do with these unstable atoms of the mercury, and you couldn't do it any other way, was to try and answer this sort of problem. And indeed then, that's in the fish. Well, if you've got a big fish like a tuna, which then goes and eats a fish, and you ran through the same sort of thing, then the amount of methyl mercury you would expect to end up in the tuna, and the tuna's got an awful lot of muscle, that over 99% of that mercury would end up as the methyl form. It would be in the muscle, and because it's a big fish, it would have a very slow excretion rate. And that's why tuna have got an awful lot of mercury in them. It's got nothing to do with pollution. It's simply by the kinetics of handling these two things, which again, you could only solve if you knew something about the unstable atoms. This business of selective absorption actually became quite an issue in relation to various radioisotopes through human beings eating fish, whether it's contaminated or not. And one of the big things was the winkle. Any people eating winkles? I can't really see that there. There were people along the Sellafield coast that really loved eating winkles. Never really turned on to it by myself. It reminded me of an old postcard, Cornish postcard, when fishing was very, very poor in Cornwall. Then the fishermen literally had to scavenge the rocks and eat winkles and limmets. Back in Victorian days, this is one of the postcards you got if you went on holiday in Cornwall. We'd like a pennyworth of limbus Madeira, a bit of salt and vinegar to go with it, which is relevant because we wondered what was the gut absorption of the plutonium and the americium from eating winkles. Most of the experimental information was about pipetting it down into rats. So well, we do it ourselves, right? Did a few calculations and worked out, well, if you could eat about 0.5 kilogram of winkles in a day, you could probably look at the gut absorption in humans. So a few of us decided to do that, and loads of winkles, this winkle flesh was gathered from a round wind scale, frozen, sent down to the lab, thawed. If you've ever smelt a walrus close up, it's very, very similar to that. 0.5 kilogram of winkle flesh. So I thought, well, I had 1/3 of it on toast for breakfast and managed to keep it down. I had 1/3 of it with brown bread and butter and salt and pepper for lunch and managed to keep it down. I still had 1/3, and I thought, the hell with it, I just took handfuls of it and swallowed it with a bottle of beer. That's just the beginning, however, because you then had to collect all of your urine for the next week or 10 days. And it's fine. It's quite interesting, really. Except you don't know what to do with it as it builds up. I used to take mine to the lab and put it in the windowsill every day. You got bottle after bottle of urine. And when the sun shone through it, the colours are quite wonderful. And the volume, because it's not related to what you drink, it's the amount of water content of your food and so on. And I commend it to you if you're on holiday and you're bored to tears for a week. Just get everybody in the family to collect all the urine for the week, put it in the windowsill. And, I never took a photograph, unfortunately, but I'd like to have done. It so happened that one of my colleagues who was taking part in this experiment, after about a couple of days, suddenly had to fly to Brussels, I think via Amsterdam, just for a short meeting. So he took his bottles with him, of course. Coming back through this little provincial airport, this is back in the days before 9/11, he was carrying his urine, and the customs officer said, "Oh, where have you come from?" "Amsterdam." "What's in your bag?" Right. Well, he explained what it was. Would you have believed it? Why would you come back from Amsterdam carrying your own urine in a bag? So it took a bit of explanation, I can tell you. It was worth it, because we did show that the other numbers were incorrect, and after that, the numbers we used were correct. In fact, they'd allowed for the organically bound plutonium to be absorbed quite well, but because it was still mixed to the sediment in these things, the absorption wasn't as much as one might have thought. So, why did we do all of that? What's the effect of radiation on people? Let me get on to the DNA. I mean, an awful lot of people are scared about it, and really scared about it. There's no reason to be. I think the effects of radiation, particularly in relation to human beings, are better known than anything else. And let me just perhaps run you through a bit of it. First of all, you need to appreciate the difference in the types of radiation. As I said, you've got alpha particles, beta particles, positive and negative, and gamma rays. Alpha particles you can stop with a sheet of paper. Beta rays, sheet of aluminium. Gamma rays, a chunk of lead. In other words, they penetrate at different rates into biological tissue. The units that we use for this, just to remind you, radioactivity, the quantum amount of radioactivity is a becquerel. You don't get irradiated with radioactivity, you get irradiated with radiation. Radiation is measured in terms of absorbed dose. It's the amount of energy that's absorbed by something. The absorbed dose is the grey, which is joules per kilogram. But because of this different penetrating, a different power of the different particles, we alter these numbers. We allow for the different what we call different radiation weighting factors. So the alpha particle is judged to do 20 times more damage than other particles. Then, of course, it depends on where it's going in your body, because what you can be worried about, particularly, is cancer. Now, different organs of your body are differently susceptible to cancer, and different radioisotopes, of course, by the chemistry, will go to different parts of your body. So you have to allow for that as well, and that is done. So we have the absorbed dose, the basic dose, the equivalent dose, the effective dose, which allows for all of these. Both of the latter are measured in sieverts, but by and large, from what I'm going to say now, it's going to be in sieverts. And don't say all these different sort of radiation. Don't say whether it's natural or artificial. Don't say it goes here, it goes there. All of that is normalised. It's all allowed for. So you can actually do it on a comparative basis. In terms of radiation effects, there's a very strange body, of which I have to say I'm a member, called the International Commission on Radiological Protection. And they look at all the science, and they advise all the UN bodies, the IEA, UNEP, the International Labour Organization, World Health Organization, and so on radiation standards in all aspects of radiation. So it's diagnostic and therapeutic medicine, radiation exposure of workers, radiation in the public, and more recently, radiation in the environment. And essentially, you can look at radiation. High doses, it causes what you call deterministic effects. It kills cells. You can actually get tissue reactions. Below that, it's simply a stochastic process. There's a risk of getting cancer. At the very low dose rates, there simply isn't the evidence. But we use something called a linear no threshold model and extrapolate down to the very low dose rates. Some people say we should reach a level where there's simply no effect when you call it zero. We don't. For prospective dose purposes, we think it's more conservative to do it this way. The danger, of course, is these alpha particles, beta particles, gamma rays and so on can disrupt DNA, although DNA looks like. And it's the double strand break. If it just does one break, it repairs quite quickly. But if it literally chops the DNA in half, which it can do, it'll repair itself, but quite often it misrepairs itself, and this is where much of the damage is done. The other thing to bear in mind, of course, is you always see DNA like that. It's this sort of model. Actually, the DNA is quite an active molecule because it's interacting all the time with our RNA. So the DNA molecule is actually spread out and shaped in all sorts of different ways, and these particles are belting through it and damaging it or not damaging it, as the case may be. Not terribly well known, but it's been extremely well studied. What we do know, more or less, is the response of the human animal to different levels of radiation. We know it from medicine, Hiroshima, Nagasaki, all sorts of things. To kill somebody, you can, this is millisieverts, millionth of a sievert, you need about 4,000, you need about 4 gray. The poor souls who died in relation to the H-bombs, Hiroshima and Nagasaki, but also in relation to Chernobyl, the people who went in to try and rescue people. Some of them got these very, very high doses. What the radiation kills are the cells which are going to reproduce quickly, so the gut lining, the lung, white blood cells and so on, and it's the after effects of that kills them. Acute radiation syndrome, about 1,000 millisieverts, you can survive that, and they do. With the right medication, you get through that. The annual dose for emergency workers, which we've just had in relation to Fukushima, you can let them up to about 250 millisieverts, pretty high risk. The risk being of stochastic effects. Don't worry about cancer in 20 years' time, but the actual damage now. And to intervene in these situations, we recommend about 100. So it gives you a feel for these numbers. If you're working in the nuclear industry in the UK, your annual occupational dose would be about 20 millisieverts maximum. You'd be lucky to find anybody who gets 2, but in theory you could go up to about 20. And at that level, you've got an assumed cancer risk of about 0.1%. Bear in mind, you've got a cancer risk of about 33% anyway, so this is additional to that. So you've gone from 33 to 33.1, not a lot. I mean, cancer by and large is a disease of old age, because naturally the DNA is being damaged in all sorts of ways, repaired, misrepaired, and so on. Eventually, it's like Chinese whiskers. Like, you see a newborn baby, it's absolutely wonderful. You see an old soul like me, I've had so many cells reproducing, all this collapsing. If you go to hospital, you get a CAT scan, you get about 8 millisieverts. The average background dose here in the UK is about 2.4, pretty variable. In terms of the deliberate exposure of the public, as like the Sellafield and the Winkles that I was talking about, the dose limit above the background for the public is 1 millisievert, and that's in total. For any particular plant, say for an individual nuclear power station, it's 0.3, and what people actually get around the UK is that number. It's an absolute fraction. This is millisieverts, all right? Looking at the average dose, I mean, 85% is natural anyway, not from the sea, but from particularly the soil that you live on, the radon in the air and so on. Quite close down here. Nowadays, of course, medical radiation provides you quite a lot. Used to say background dose is about 2-ish, but now the more and more use of radiation in medicine, we'd say the average dose is now about 2.6. And if you look at it around the UK, it's quite interesting. It goes from 2, sometimes lower than 2. As you come down here, it goes up and up. The average for Cornwall's about 8. Where I live, it's probably about 16. And it used to fascinate me talking to people up at Sellafield. I don't like that terrible nuclear power station. I'm moving away from that, all the radiation. Oh, where are you going? I go to Cornwall. Oh, go. So here, you by law, you can't go from 2 to 3. You go to Cornwall, you probably go up to about 15. But but that's natural. It's green radiation. It's organic radiation. It's whatever it is. There's radiation. You're hit by a bullet. You're hit by a bullet. Doesn't matter who fired it. And you can never get this message across. So what's this got to do with the price of fish? Well, if you look at something I was always asked when I was interviewed in Lewiston, whatever the subject, what's it got to do with the price of fish? Or how will it affect the price of fish? If you look at the dose that people who are the high seafood consumers around Windscale, they're still the highest in the UK, then they are at the moment going up with 2007, I haven't bothered to update it, just over 0.2 millisieverts a year. Now, one of the things I was quite interested when I was working on this subject is that bottom circle is wind scale and the stuff coming out of there. Just around the corner, there was the Marchand plant, which imported phosphogypsum, and was making phosphoric acid. Phosphate was very high in uranium, and therefore it's full of all those unstable atoms from 92 down to 83. And this was also going on. And particularly in marine organisms, they seem to accumulate a lot of polonium-210, an alpha emitter, polonium-210. So I did some measurements around there, trying to work out what their dose was. And I thought, well, actually it's damn sight higher than what's coming out of Sellafield. And me having eaten all the Winkles to try and find out what that absorption dose was anyway. And indeed, I was quite interested to learn fairly recently that there is still a residual around there. I'll show you that first slide again. It's peaking around between just over 0.2 millisieverts a year from all of the stuff coming out of this big nuclear reprocessing plant. And around the corner, literally around the corner, from the residue, because the plant closed down about 10 years ago, from the residue, the excess polonium that's come out of that plant, getting into the seafood, which the people are eating, you can see it's 0.2 in excess of 0.3. They are still getting a higher dose from the naturally occurring unstable atoms in the phosphogypsum they were from the nuclear power plant at a huge reprocessing plant just around the corner. Now then, finally, we know pretty well, I'm never the slightest bit worried about exposure of people to radiation. As I say, if we were wrong, we'd be wrong in every hospital in the world, because that same knowledge is used 24 hours a day all over the place. But what about the impacts on the rest of the environment? The natural environment, and particularly the marine environment, has very, very high levels of naturally occurring radioactivity. That naturally occurring radioactivity gives marine organisms quite high dose rates, quite considerably high dose rates. And then, of course, you've got other things happening as well. For human beings, we have lots of points of reference for dosimetry, for dose effects, and so on. We never had anything for any other animal or plant. We now do. We have sets. And for the marine environment, we simply have a set of 3. We have a flatfish, place. Guess why? The crab, not the lobster, and the seaweed, things that we've worked on. These are now the international reference points for looking at how to calculate the dose and what the radiation effects would be. We have something called derived consideration reference levels, which I won't go into, but the bands of dose. For any discharges, you must be below that band. But if something goes wrong, then you can relate it to that band. And that's what's being done at the moment in Fukushima. My next trip in about 4 or 5 weeks is out to Fukushima. Enormous quantities of radioactivity went into the sea. And now looking at what the doses were to the marine life and how they relate to what effects could have been. Quite a complicated situation, but which I haven't got time to tell you. But the other thing that's always fascinated me is, what about these naturals? For the human being, we know in relation to the radiation dose and the tissue what the risk of cancer is, but it's simply related to us. So what about these animals that live out there with these very high levels of polonium-210, the alpha emitters? You've got a blue whale. Well, a blue whale has got, what, 0.1 times 10 to the 10 cells. Got an awful lot of fat, of course. And there's about 10,000 times more cells than a human being. So it brings me back to my original, where's the theory in this? If these double-strand breaks cause cancer and they're caused by radiation, this will lead to a ton of krill at a time, which is full of polonium-210, full of all these alpha emitters. Where does it go in the animal? What's the dose that it gets? Because for things other than human beings, we don't multiply it by 20 for alphas. There is no international unit like the sievert for anything other than human being, even though the biology tells us otherwise. There's no agreed way of actually expressing the dose. You can only do it in grays, therefore perhaps be wrong by a factor of 20. So what tissues would it go? Is it related to the tissue, the reproduction rate of the tissue, the number of cells in a lifetime of those tissues? So if you looked at these things, would you actually find anything? After all, the blue whale, lifespan of 80 to 90 years, longer than us. There must be a bit of theory here. So I've been trying to find out, for people who do autopsies and so on of marine mammals, do you ever see cancer? And in the UK, they've done autopsies on about 3,000 marine mammals, and they do see cancer. They found 10. Oh, toasted tissues from Plymouth. Oh, I've already said that. What are the cancerous? Yeah, they found 10, and all 10 have been in the porpoise. They found cancer in anything else. I'm not quite sure why. Why in the porpoise? Or why not in anything else? Have you looked in the right things? Again, where's the theory in this? It's still a big area there that needs looking at theoretically and then doing experiments and the observations to see if it fits the theory. Either they do or they don't, and if they do or they don't, it's very interesting as to why they do or they don't compared with anything else. So it's still, I think, a young subject that needs to grow. So, in conclusion, studying unstable atoms is fun, I think, and informative. I don't know if it's informed you, but tells you an awful lot about the way the world is. I always think with chemistry, oceanic chemistry and so on, it simply relates to the electrons and things. Looking at the world not through the stability of the atoms, because if they're all unstable, the world will fall apart. But most of the way we look at environmental chemistry is because of the stability of the atoms. If you go to bit one side and look at the world through the instability of the atoms, it casts it in a whole new way, which is rather interesting. It's an area, as I've just said, of science that needs greater breadth and interface of theory and observation, I think. Fascinating range. We've gone from quarks, subatomic particles, to blue whales. You know, you can take in anything with it. It's a very specialised area, but as I say here, I think the knowledge and expertise is still essential because we need more nuclear power. We're not going to exist without it. Of the nuclear power we've still got the waste. We haven't got rid of it. We'll still have accidents. There'll be more and more power stations, more and more countries, and things are likely to go wrong. And in dealing with it, we need a sense of perspective. Otherwise, people get panicky over all these things, and that's absolutely ridiculous. So, I had thought when I'm beginning this talk, perhaps I should dedicate it to somebody, but then I thought it might be such a dreadful talk, it seemed a bit presumptuous. So, I'd just rather thank. These are the various laboratories that I've worked with over the years. So, thank you very much.